Bismillah Rahman Rahim. Welcome students to the online lecture of digital logic design. In the today's lecture, we will be discussing the adders and their circuits. In the previous lecture, we started the combinational logic section. In the combinational logic part, in the today's lecture, we will be discussing the binary adder circuits. This part also belongs to the course learning outcome 3. First, we will try to design basic adders for the system. We will start with the adders, then we will move to the subtractors, and then the multipliers and the other hardware. Because for any given digital system, one of the main functionality of that system is to perform arithmetic computation. If you consider a CPU, normal central processing unit or a processor of a PC, desktop PC system, one of its important tasks is to perform different arithmetics. Generally, these are performed through a certain arithmetic logic unit, or we call it as ALU. So in this part of the lecture, we will be dealing with the hardware of these sub parts included in the arithmetic logic unit. That we have already studied that how we can add 2-bit numbers. So now we will be seeing or discussing that what kind of circuit is required to implement these processes in the hardware. So these processes are actually the part of any hardware processor. So we will be discussing how we can develop different kinds of adders, subtractors, and the multipliers. One of the most basic adder is the addition operation between two single bit variables. Say x and y are two variables. We have to perform the addition part in that. As you remember, if we have a 2-bit number, we can have multiple types of results. Say if both of the bits have value equal to 0, then we would have result equal to 0. If we have one value equal to 1, then the output would be equal to 1. And when both of them are equal to 1, then the final output is 102. In this case, you have to remember a few things that now, because we are dealing with the arithmetic, so this plus sign here, it is actually representing the arithmetic plus. No, it is not representing the OR operation. It is actually representing the plus or the addition operation. And you can also see that when we have to add two single digit number, the result could be represented in n plus 1 bit, or it could be accurately be represented in n plus 1 bit. So for the two single bits we are adding, we need to represent the correct answer in form of 2 bits. So 2 bits are required to represent the operation. Just like in this one, if you see that when we are adding both the 1 and the 1, then our result is represented in form of binary equivalent of 2. And for the representing binary equivalent of 2, we have to represent it in form of 2 bits. So we require 2 bit to represent the answer. And then the next process is the same, that if the digits are more than single bit, say if we have two binary numbers, say each is representing a 3-bit number, then what we do is we first solve or add the first column, and then we see that if any carry is generated, then we transfer that carry to the next column, and then we perform the addition accordingly to that column, and then after that we move to the next column. So we will in the same way we will try to implement or design a hardware that could implement the basic addition process of a given binary numbers. Most common or simple of the adders is the half adder. In the half adder system, we have two single bit input lines. We represent them as, say, one is X and the second one is Y. As we have discussed in the last slide, the result of these 2 bit could be represented in form of two output. One is the sum and the other is the carry. So the 2-bit numbers have two inputs x and y, while the half adder will have output of sum and carry. And sum and carry we here are representing the two outputs here. We are representing sum as the capital S and the carry as the capital C. This is the main block diagram of a half adder system. Now we will try to design a hardware for this system. If you see the truth table for this one, then it's very easy. We have already seen it, that if you have two inputs x and y, then we will be getting the result in two bits, sum and carry. When both of them are 0, we will get sum as equal to 0, and it would also generate a carry of equal to 0. When any one of them are 1, then we will get sum at the output. Again, the carry will be remain 0. When both of them are equal to 1, then we have sum equal to 0, while there is a carry of 1 is generated or transferred to the next column. So to accurately represent this process, we need to represent it in a 2-bit output. So we have represented it in form of sum and carry. Now, if we represent this whole process, or you can say we can design a hardware for this process, then we can easily design a hardware for this time using this truth table. Because if you see this truth table, you know that for this sum part, if you see the outputs of the sum, these outputs resemble to the exclusive OR operation of the two inputs. So for calculating the sum is equivalent to exclusive OR of the two inputs, which is represented as this one. We can also represent it in a form of AND on OR gate in a form of this one, or more conveniently in the form of an exclusive OR gate is this one. And if we want to implement the circuit of the carry, then you can see that the carry circuit resembles a simple AND gate operation, in which when both of the values are equal to 1, then only then its output is equal to 1, otherwise its value is equal to 0. So from here you can also see that it is very simple, that the carry is generated as just the AND of the two inputs, while the sum is represented as the exclusive OR of the two inputs. So if we represent them in the form of a logic diagram or circuit diagram, we can easily represent them. We have calculated these equations from the last slide, and you can see that this represents the equation of exclusive OR in terms of AND and the OR gate. So if we want to represent the sum in the form of AND and OR gate, we just represent this Boolean expression, and it is represented in a way that there are two AND gates involved and one OR gate. So these are the two AND gates, and this is the OR gate here. So this will give us the sum. We are assuming here that we are getting the values of input in both the complemented and the uncomplemented form. Similarly, the carry is generated by just the AND operation, which is represented here as this. We can again, because this expression here represents the exclusive OR operation. So instead of the AND OR gate, we can just use a simple exclusive OR gate here too, like this one. So if we replace this AND OR operation with an exclusive OR gate, it will be representing our sum, while the AND gate will be representing our carry term. For the half adder case, we have seen that the half adder is used to represent the addition process of 2 bits. We have a 211 bit number, and then we can use the half adder to get the result in the form of sum and the carry. But if you remember the whole procedure of solving a given n bits number, or the addition process of any given n bit numbers, we know that we have to follow a column wise approach, in which we move from right to left, starting from the least significant bit to the most significant bit, and we solve the addition process by column and then transfer to the next column. So when we are adding the two numbers in the form of, say, columns, we always have to adjust another input, which is the carry in input, because after the first column there always could be a carry that could be transferring from the previous column. So for considering that extra bit, we need to represent an extra input in our system. So that input is generally represented in a form of an other input, we represent it as a C in or C carry or just another variable, say as Z. So a full adder is an extension of an half adder in which we are now dealing with a three input system. Now, because we are having a three input system, the first thing that is required is we draw a truth table for it. So what we do is we simply draw a truth table according to the three input x, y, z, and then we calculate the again the sum and the carry terms. The process or the basic thing remains the same, because when we are adding the or summing the three bits, whenever we have a single one here, it will correspond to a sum of 1. When we have two ones in the input, that would be corresponding to sum equal to 0 and carry equal to 1. While if we have three ones in the inputs, just like in the last case, in this case we will have sum equal to 1 and carry would also be equal to 1. So in this way we solve the three input addition process, and result is achieved in form of two different bits. First is the sum and the second is the carry. So just if we try to perform the or minimize the expression of sum and the carry, what we do is we follow the k-map technique. First we use the s as the system output and put the 1 in the k-map according to the places where we have 1 here, or the we get the addition equal to 1. So for all these main terms we put the 1 here, and when we try to minimize this term, we can see that there is no minimization could be achieved because we don't find any adjacent squares here. You can easily see that there is no adjacent squares here. So we cannot further minimize this term. So what we can do is we can just OR all these four main terms here, just like this. And for the carry term, what we can do is we write all the ones here which are at M3, M5, M7 and M6, and then we see that how we can combine them to represent the minimized expression. For representing the minimized expression, we can form a different combination of two adjacent square. One is this one, and then we can combine these two and then these last two. So this will result in this expression. So in this way we can achieve that the carry circuit can be represented in this way, while the sum circuit is represented as just the OR of four minterms. Now, if we want to just represent in the form of an circuit diagram, what we can do is that it is because in the form of sum of product form. So what we do is first we calculate the products. So these products are calculated as using the AND gates. So first we calculate the four products here, and then we OR them to get the sum term. So these are just the four main terms we have calculated, and then we OR them to get the sum result. So this is equal to representing the sum. While for the carry one, we have again is in a form of sum of product form. So these are the products, three products we calculated, and this is the OR of these expression or sum of this expression. So this is representing the carry. So this is the standard diagram for representing a full adder in a form of sum and the carry one. So this circuit is utilized to perform the addition between three input system, because in the three input is we are considering two inputs x and y, while z is considered as the carry in, which is also act as an separate input. So it is representing the third input of the system, and we are getting the result in form of 2 bits. So in this case we are getting the result in the form of 2 bits. So far we have represented the full adder in a form of different sum of product expression. These expressions were obtained from the directly from the k-map. There is an other way to represent the operation of an full adder. It is by combining the two half adders in a way that if we combine the two half adders and put an extra OR gate in it, then we can also represent another full adder. The representation is a bit different, but the result is the same. So what we need to do is first we calculate the carry, and how we can calculate the carry is because we are using the two half adders here. So the result of the first sum is exclusive OR with the third term. So in this way we will get the sum term here. While for the carry, what we do is we OR the carry of the two half adders here, which will give us the equation for the carry. This circuit is generally represented in this kind of diagram. This dotted line is representing first half adder, while this dotted line is representing the second half adder. And you can see that this is the Z is the third input. First, what we do is we just perform the half adder operation for the 2 bits, and we get the result here of this. This is the actually this point gives us the result of the first half adder. This result is fed into the input of the other half adder, and the next input to this is the third input, which is a Z variable here. So this will give us the final sum as the exclusive OR of the or of 3 inputs, X exclusive or Y exclusive or Z. So in this way we will get the sum here. And how we get the carry here is that that for the first half adder output, we OR it with the output of the second half adder. So in this way we will get the carry term here. And if you can express it, you want to express it, you can express it in this form. So this is another way or alternative way to represent a full adder. This is using the cascaded form of two half adder. This is the first half adder, you can say it is the first half adder, and this is the second half adder, and combinedly they are representing a full adder operation. Now, so far what we have done is we have tried to add few numbers which are representing a single bit. First we discussed the half adder. In the half adder, what we had was two single bit numbers X and Y. We added them. And in the next part, we also included the carry term, which was represented by the Z. So in that case, in a full adder, we represented the addition process using a 3-bit input system, and both of them, the result was represented in form of two outputs. One was the sum and the second one was the carry. Now we will be trying to further extend this concept into form of different numbers. We have now so far taken X and Y as single bit. What if X and Y are representing multiple bits? Say X and Y is representing a 4-bit number or a 5-bit number. Then how we can use these adders, full adders and the half adders to do the addition process? Say in this example, we have considered two numbers. Say first one is the A. It is a 4-bit number, 1101. While B is the second number, 1100. So we need to design a hardware for them for their addition process. And we will be using the same concepts of half adder and the full adder, which we have just studied. If we just first we draw the table like this form. In this we have written the two number here, the augend and the addend. This is the A and this is the B here. The each bit of is represented as AI or BI, starting from the say subscript 0, then moving on to subscript 1, 2 and 3. So i's is representing the values from the least significant to the most significant. We are also considering the carry here too. For the first case, for the first column, we would be considering a 0 carry. And from the next one, what we will get from the carry is will be based on the result of the first column. So we will try to solve it column by column. So for the first column, if you just solve it, because in the first case the carry is considered as a 0, the value of A of 0 is equal to 1 and B of 0 is also equal to 1. So if we add them, we will get sum equal to 0, while we will get, and the next carry would be equal to 1. So in this case, we will getting the next carry as A equal to 1. So which will we get here? So this is the carry generated here. And now we will move to the next column. In the next column, the A1 term is equal to 1, while B1 term is also equal to 1, and we have a carry of 1 here too. So in this case, both we have sum equal to 1 and carry for will be also equal to 1. So again, this carry will be transferred to the next column. Now in this column, both the values of A2 and B2 are equal to 0. So their sum would be equal to 1, while the next carry would be equal to 0. So for the last column, there is no carry. So in this case, we will have A3 equal to 1 while B3 is equal to 0. So this final result will be equal to sum equal to 1, while the last carry that or the output carry that is generated would be equal to 0. So in this way, by column wise, we perform this addition. Now we will try to develop a hardware for this whole process, that how we can develop an hardware using the half adders and the full adder to simulate this process. If you just represent or try to solve this example through the simple truth table process, then we have seen that we are having two 4-4 bit numbers here. A is represented in 4-bit. Similarly, B is also represented in 4-bit, and we are also having a 1 bit of carry. Say this is the carry, original carry, and this is the A, and this is the B. So we have a total of say 9 bits here. So if we want to represent these 9 bits or perform the addition of 9 bits, or what we need to do is we have to calculate the 2 to the power 9 entries for this one. We have to calculate 2 to the power 9 entries to solve this thing here. And you know, for the 2 raised to power 9, which is equal to 512 entries. So if we just follow the traditional method and try to develop a hardware for this binary adders of two numbers of 4-4 bit each, and also considering a 1 bit for the carry, then we would have to develop a truth table that is have 5 and 2 entries. And then we have to check all the values where we get the sum or carry is equal to 1, and then accordingly we have to design the hardware. So you can see that it is a very complex thing to develop, and if the bit number is increased to 1 bit, say this is 5 or 10, then it will become even more complex. So we have to define an efficient strategy or hardware so that we can easily implement this thing. So we implement this circuit in a way that what we do is we follow a cascaded approach of different full adders. This is each box is here is representing a full adder. What we do is first we consider the carry is 0, C0 carry or the initial carry, and these are represent the first bit of the two numbers that we have discussed. We just add the first two numbers, and the full adder will calculate two things. It will first calculate the sum at this bit and the carry at that bit. So when this carry is generated, then next operation will be performed, and for this operation what will have, it will perform the addition between this A1 and B1 bit, and again it will produce result in form of 2 bits. One is the S1 and second the carry, and carry is generated here as the C2. Similarly, when this carry is calculated, then we simply have the full adder here. In this full adder, it will add 3 bits A2, B2, and considering the carry C2 here, it will generate the two outputs, the sum bit and the carry bit here. Similarly, when this carry is generated, then this full adder will be activated, and this full adder will calculate the again 2 bits. One is the sum and next is the carry, and this carry will be the overall carry. So to represent or to add 4-4 bits number, 4 bits number, we required a hardware which consists of 4 full adder. This is the first full adder, second full adder, third full adder, and the fourth full adder. So to represent this system, we represent this in a form of a cascaded system. which involves 4 full adder, so we can represent them in a form of a full adder. And as we know, for the first case, the carry in or C0 is always equal to 0, because there is no extra carry in for the first column. So if what we can do is, then if we consider it as a 0, then we can just represent this as an half adder too. So for the first one we can use the half adder, and for the all other we have to use the full adder. So we can use this full adder to represent the effect, because the carry is first transferred to the first here, because the carry enters here, then it moves on to the next full adder, then to the next, and then to the next. So carry is basically moving on from the one case form of one full adder to the next, and then. So that's why this circuit is also known as the ripple carry adder 2. So in this ripple carry adder, it is used to perform the addition of two 4-4-bit numbers, where both A and B are representing the 4-4-bit numbers, and we are also considering the carry in here. So it's total, it's representing the addition of, you can say, 9 bits. The first we can change it to the half adder, because for every number C0 must be equal to 0, so we can replace the first full adder as the half adder, and we have to represent all the next as the full adder, and this will be the carry of the overall term. The final term, final sum will be represented in form of 4 bits: S0, S1, S2, S3, and then S4. The process is the same which we discussed in the last slide. We only now need to represent the system in this form. Kindly do read these pages from the this book. We will be continuing with the same topic, and we will be discussing a few circuits or few techniques to improve this ripple carry adder hardware in the next lecture. Thank you.